We're going to start this lesson off. This is a lesson that combines dots factoring with greatest common factor. Now, dots is an acronym that we'll get to here in a second. Our first one, I want to go to a little bit of review. So if I look at something like 4x to the fifth minus 3x cubed plus 14x, like we did in the last lesson, we're going to look to see what's in common. 4, 3, and 14 have nothing, but x to the fifth, x cubed, and x all have an x in there. So I can put parentheses around this and reverse distribute an x out, leaving behind a 4x to the fourth minus 3x to the second plus 14. This gives me a total of two factors. You remember you have to see this x as being no different or no more or less important than this one here. Those two highlights are our two factors that are remaining from that factoring. Look at number 2. 8a to the second bc to the second minus 12a b to the second c to the second. This is a polynomial made up of two terms. Put parentheses around there and we start to look for what we can take out. Let's look at the constants, the 8 and the 12. I can take a 4 out of that. Look at the a's, a squared and a. I can take an a out. B and b squared, I can take a b out. And c squared and c squared, I can take a c squared out. If I take that out of the first one, I'm left with a 2, because 2 times 4 is 8. I'm left with an a, but the b's go and the c's go. And then I'm take out a 4 from the 12, I get a 3. The a's taken out, the b's, there's a b left, but the c squared's gone. So this is a case where reverse distributing actually ended up with what looks like a simpler form. It's really not. This is a factored form. And I really want you to look at this and see this in the sense for what it is. This is actually the same thing as 4 times a times b times c squared times 2a minus 3b. And if I really brought it down to its prime factors, it'd be the same thing as 2 times a times b times another c and yet another c and then 2a minus 3b. Count them up, 1, 2, 3, 4, 5, 6, 7. There are 7 distinct factors there. Some of them are identical to each other and some of them are not. The 2a minus 3b is a done prime factor. It can't be factored anymore. But your answer to this one, when we say what do you get when you factor it, is this thing. We're never going to show this thing over here because we don't need to. That's just for your benefit because these are notes. Okay, let's go to number 3, our last of our little intros before we get to dots factoring. I have 27t to the third minus 18t to the second minus 36t. And I'm going to actually put that over negative 9t, and I'm going to change the directions from this one. Whereas the first two might have been a factor, this one's going to be a simplify. It's a very similar process because I'm dividing by a negative 9t, and I can actually use the distributive property of division, which is the same as the distributive property of multiplication. Divide it there, divide it there, and divide it there. Because if I'm going to divide it to one spot, it has to divide to all spots. If I divide it to the first part, 27 over negative 9 is negative 3. T to the third over t is t to the second. Divide it to the second, negative 18 over negative 9 is positive 2. T to the second over t is t. And then the third term, negative 36 divided by negative 9 is positive 4, and the t's cancel. So I'm left with a polynomial that's roughly the same. Actually, this polynomial is 3 terms. It's a simplified form of what I started off with. That is, of course, assuming that this t in the denominator was not equal to 0, which is an important thing to consider. So I'm going to put a little break line and kind of go to our new part. Many ages ago, a long time ago in a math class, well, last semester, we learned about multiplying conjugates. This is important because conjugates, this is a term you need to know, conjugates are binomials that differ in the middle sign. For instance, in a general form, the conjugate of a plus b is a minus b. The conjugate of 7x plus 4 is 7x minus 4. The conjugate of 1/2 x squared y minus z is 1/2 x squared y plus z. Hopefully you get the idea that all of those are conjugates. But what I'm going to do now is I'm going to take each of these respective conjugates and multiply them by each other. I'm going to put little directions here on the left. We're going to say multiply. So if I multiply I need a numbering system. Let's just put a dot here. If I multiply the first one, a plus b times a minus b, I get a squared minus b squared. My outer and my inner cancels. We practiced this. This was actually on the last test. A test that when I record this, you guys will be taking tomorrow. But anyway, if I do the second one, 7x plus 4 times 7x minus 4, I get 49x squared minus 16. Multiply these two. 1/2 times 1/2 is 1/4, x to the 4th, y to the 2nd, minus z squared. And just as review, if I do 2 to the k minus 4 times 2 to the k plus 4, when we multiply with the same base, we add the exponents, but we don't change the base. That would be 2 to the k plus k, or 2 to the 2k, minus 16. Those are multiplying. What we're going to be doing is actually going from the right side and seeing if we can go to the left side. Now what I want you to do is actually look at these right sides here for a sec. The a squared minus b squared, if I know I'm going to conjugates, and I know I'm going to something with a plus minus, it shouldn't be too hard to get to a plus b, a minus b. So we're going to kind of separate this out, but this pattern, these things that we see circled in, I'm going to do a little better job now of circling them in this purplish color highlighter. This pattern here is called a difference of two squares, or dots. I'm going to define it here in a sec. So I'm going to define it right now. Difference of two squares. Three conditions must be met. Three conditions must be met. We will say condition 1. It must be a binomial. So binomial is something like x plus y. It must be a binomial. Condition 2. The first term must be a square. It must be something square. Condition 3. Actually, let's go 4 conditions. I just miscounted. The second term must be a square. And then lastly, condition 4. Yeah, I lied. Sorry. Fourth condition. I forgot the difference part, and that's important because it kind of characterizes the whole thing. There must be a minus sign. It must be an actual difference, meaning subtraction. Don't worry, that's about all the writing that we have to do in this thing. So, must be a binomial. First term must be a square. Second term must be a square. And then lastly, it must be a difference. So on the right side here, I'm actually going to show you 4 examples of where this is not true. If I have x squared minus y squared minus z squared, that is not a binomial, that's a trinomial. First term must be a square. Sometimes people think if I do 2x squared minus 4, that's going to be a difference of 2 squares, and it's not because of the 2. Same thing with the second term must be a square. If I go 49 z to the 4th minus 2, that's not a difference of 2 squares because the second term is not a perfect square. 4 must be a difference, meaning subtraction. If I do something like this, I go x squared plus 16, that's not a difference, that's a sum. I'm going to rewrite this middle one here in red so you can see that that was a bad example, not a good example. So all those in red are bad examples. Those are not differences of two squares. So what are differences of two squares? Well, let's do a couple. Here's the real number one. This is the meat of this thing. Difference of two squares factoring. Your directions for the rest of these are to factor completely. Here's one, 100 minus t squared. That is a difference of two squares. 100 is 10 squared, t squared is, well, t squared. I'm going to separate that into two binomials. So it meets all four conditions. First term's a square, second term's a square, it's a binomial, and it's a difference. When it's like that, we're going to separate them. We're going to take the 100 and split it up into the two numbers that multiply to get 100 that are identical, 10 and 10. For that matter, we're going to take the t and make it t and t, and then just a little plus, minus. That is fully factored. That's it. Number two, 64 y to the fourth minus 25 z to the second. Just do a quick scan. Are both of those perfect squares? Yep. Any even power is a perfect square, so 64y to the fourth factors. We set it up with a little plus minus. 64 comes from 8 and 8. Y to the fourth comes from y squared and y squared. 25, 5 and 5. Z squared comes from z and z. That's all there is to it. Number 3, if I go x squared minus 1, that may not look like a perfect square, but 1 is a perfect square. So, difference of two squares. Plus, minus, x squared becomes x and x, and 1 becomes 1 and 1. X squared minus 1 factors into x plus 1, x minus 1. Now, I'm going to do a little one I'm going to call 3a. We're going to do it off to the right here. I'm going to do x to the fourth minus 1. Same idea, x to the fourth splits up into x squared minus 1 and x squared plus 1. But that's not fully factored. If I look to see what x squared minus 1 is, that's also a difference of two squares. In fact, we just said it factors into this thing. So what I have to do is I have to take this and split it up even further into x plus 1 times x minus 1. Then I take this thing and I just kind of bring it back down as x squared plus 1, because that is a sum, it's not a difference. And that part's done. In that sense, this looks a lot like a factor tree, where I ended up with 3 possible factors instead of 2. Number 4, if I go x to the fourth plus 1, because it's a plus, we get to say that that one is prime. And I'm going to put little parentheses there to show you that we can't do anything with it. Number 5, let's do 72 x to the fifth minus 2x. This does not satisfy the condition of the first term and the last term being perfect squares. But now we have to kind of go back to an old adage. GCF first. Strictly speaking, on each of these I should have been looking to see if there's a greatest common factor I could take out. And here there's definitely something. I have a 2 and an x. If I take out a 2 and an x, I get 36 x to the fourth, then minus 1. Oh, sorry, not 36, not 35. That is a perfect square. So I get 6x to the second minus 1 and 6x to the second plus 1. And I have this whole thing as my factored form. Okay, number 6. I want you guys to try this one. X to the eighth minus, not 64, let's go 256 y to the eighth. Okay, 256 is 16 squared, so when I split this up into our plus minus, I get x to the fourth minus 16 y to the fourth, then x to the fourth plus 16 y to the fourth. Okay, one of these can continue, and this is a tricky part of difference of two squares, seeing that this one is actually not done yet. Can go further into another difference of two squares. I can split that up into x squared minus 4y squared, x squared plus 4y squared. And then I have to carry down the one from above that didn't factor further. The x to the fourth plus 16y to the fourth can't factor anymore because it has a plus sign. Are we done? Well, nope. That first one can go down even further. This can come down into x minus 2y and x plus 2y. And then I'm going to bring down all the stuff from before. We have the x squared plus 4y squared that couldn't go any further. And we have the x to the fourth plus 16y to the fourth. So that's difference of two squares, then difference of two squares, and then one more time until we get down to where we can't take anything out anymore. So, two things that you should always check for. 1. GCF first. 2. Are we done? Question mark. This was an are we done problem. Could we go any further? If we're done, then we're done. And guess what? We're done.